AP problem number 9. The graph below shows the results of a titration of a 25 milliliter sample of a 0.10 molarity solution of a weak acid HA with a strong base of 0.10 molarity of NaOH. A. Describe two features of the graph above that identify HA as a weak acid. As you can see, the HA starts at the pH of 3, which is above 1. Also, as it goes up, the equivalence point, which I believe it's right here, it's above 7. And also, it makes a big impact when you add the base. Now B. Describe one method by which the value of the acid dissociation constant for HA can be determined using the graph above. So we're using a fact in this one, the fact of the halfway point, which is the pH equals pKa. Since we're looking for the Ka, then we know that the P of pH equals the Ka, which is switching the other way around. And to undo the pH, we can find the Ka and 10 to the power of negative pH. Now see, on the graph above, sketch the titration curve that would result if 25 milliliters of 0.10 molarity of HCl were used instead of 0.10 molarity of HA. Since HCl is strong acid, then it's going to start at 1. And as it goes up, the equivalence point will be at 7. Since it's a strong acid and a strong base, it will neutralize at equilibrium's point. D. A 25 milliliter sample of 0.10 molarity of HA is titrated with a 0.20 molarity of NaOH. 1. What volume of base must be added to reach the equilibrium's point? Right here, I have the facts, and skipping some things, I know that there's 2.5 millimoles of HA, and that equals to the millimoles of OH. And then to get the milliliters, we're just gonna do the 2.5 millimoles of OH divided by 0.20 millimoles and times the milliliters, and we get 12.5 milliliters. The second one, the pH at the equivalence point of this titration is slightly higher than the pH at the equivalence point in the titration using 0.10 molarity of NaOH. Explain. So this is because 0.2 molarity of NaOH has a smaller volume than the 0.1 molarity of NaOH, and this affects the concentration of A-, which is the conjugate base.